Namaste everyone. Welcome to second PUC physics class. We have seen almost all the theory of series resonance circuit and we have studied even transformer. Namaste, welcome to the class. Now we have seen another thing called quality factor, the sharpness of resonance, how sharp it is in picking up the particular frequency. That means only when the input frequency or frequency of AC supply is exactly a particular value, it gives maximum current. It shouldn't give maximum current to the frequencies other than the resonant frequency. Then it is very sharp, very selective, right? And we have given a formula for that, but we didn't derive it. Of course, derivation is not very important for the point of view of theory exam, but still we will do it. Let us see how it was obtained, so that the definition of quality factor and how it is derived, why it is obtained like that, all the things we will remind. Even though you don't understand the derivation properly, at least finally you will come to know that the formula of quality factor is like this. So you know that if you draw a graph of frequencies, different frequencies along x-axis and current in the circuit and y-axis, then you'll get a graph like this. This is not a good selector. So here is current or power, then Im maximum occurs here. Out of all the peak values of AC at resonance frequency, this will be the highest peak value. When the frequency is less than the resonant frequency, same story, don't get bored, I am repeating the same sentences. When the frequency is lesser than the resonant frequency, you know that current is less. That is because of the problem from inductor. Inductive reactance will be much greater than capacitive reactance. At all the frequencies greater than the resonance frequency, capacitor blocks and capacitive reactance will be, it will be XC here, correct? XC will be much greater than XL, because XC is 1 by omega C, XC is much greater than XL, and here XL is much greater than XC, because XC, shall I write the formula here? Yeah, XC is equal to 1 by omega C, and XL is equal to omega L, 2 pi nu L. So frequency comes here in the numerator, so directly proportional, inversely proportional. Okay, but at resonance frequency, XC and XL will be equal, and we get a resonant frequency omega naught is equal to 1 by root LC, correct? Now, at that position, the total impedance of the circuit will be minimum root of R square plus XL minus XC minus XL whole square. That is what we write. We are in the lower frequencies, XC minus XL whole square, right? Now, suppose you observe a circuit like this here, which does not reduce the does not reduce the current all of a sudden. It reduces the current gradually. That means at resonance current will be maximum. At resonance current will be maximum, but if you go little beyond resonant frequency or a little below resonant frequency, current will not be zero. Current reduces to the lower values gradually. It doesn't die out all of a sudden. That means quality factor is very low. If it is a high quality factor circuit, it should be very selective, right? Like this. It is not so here. Now, if you find out here, if this is Im maximum, select a current which is at least equal to Im maximum by root 2. The peak value of current by root 2. If you select such a current, then there are two frequencies at which current is at least equal to Im maximum by root 2, and one is lower cutoff frequency, say I call it as omega 2, this one is higher cutoff frequency omega 1, and if I call this as bandwidth, half of the bandwidth delta omega, then this is delta omega, then this is omega 1, omega naught plus delta omega, then this omega 2 is omega naught minus delta omega. Hope you can all follow this. Suppose this is 500 Hertz, this frequency is 500 Hertz. At 500 Hertz you get maximum current, but current will not be zero, just below 500, say 490, 400, 300, say up to 300 if you get a good current. How much is good current? Say if this is 10 ampere, simply to make it very easy, I am giving some numerical values. This is the 10 ampere. What is 10 ampere peak to peak means? It is an AC which is passing with the highest values 10 at 10 to minus 10. Suppose you go to a frequency less than resonant frequency 300, then current will be again AC, but it will be of peak value 7 amperes. That's all. Peak to peak is plus 7 to minus 7. So this is 7.07 amperes. Sir, how did you write this value? Because 1 by root 2 is 0.707. If 1 by root 2 is 0.707, 0.707 into IM maximum 10, that is 7.07. So I think 7.07 is not a bad current, right? If out of 10, the students who have scored 10 are first rank holders, but the students who have scored 7 marks are not very bad. They are also good. So up from 7 up to 10, we can take it as fairly good amount of current. And in such a case here, so this is the 300 hertz. Similarly, again the current drops to 7.07 amperes at a frequency, say it is 800 hertz, right? Sorry, it is 700 hertz. So what is bandwidth then? From this 200, 300 to 500, to this 200, 300, 500 to 700, that is 400 hertz, that is called bandwidth. And this type of circuit is needed, I have told already, it is needed in TV communication, wherein you need a receiver circuit which will receive, that is resonance circuit, which will receive in the receiving station, which will receive a band of frequencies, which will transmit a band of frequencies, because we need to have communication with more number of frequencies, more variety of frequencies, because there are so many things have to be transmitted from the transmitting station of a TV communication station. So many things have to be communicated. So when you have so many things, you need many varieties of electromagnetic waves. Okay, let it be. This is 2 delta omega. So what is quality factor? Quality factor is the ratio of resonance frequency to the bandwidth, and this is also is equal to XL by R, or I can write it like this: omega naught L by R, 1 by omega naught CR. XL by R, XC by R, but at resonance, not all XL, XC values. Okay, this is what we are going to derive, but we keep this one as it is. So if the sharpness is more, means delta omega will be less, 2 delta omega will be very less, and quality factor will be high. So quality factor is the sharpness of resonance. It is a ratio of resonant frequency to the bandwidth. So how do you define bandwidth? Or we will go to cutoff frequencies. What are cutoff frequencies? Cutoff frequencies are the frequencies at which the frequencies at which current in the circuit is at least 1 by root 2 of the maximum value, or power reduces to half of the maximum value, right? So if you draw a graph of power versus frequency, then the graph will be like this, and this is the highest power, P maximum, and this will be the P maximum by root 2, because you know that power is equal to I squared R. So if the current is reduced from I to I by root 2, power reduces to half, because you have I squared, right? Current is I squared, power is I squared R. So any change of I from I to I by root 2 makes power P by 2. I by root 2 whole square is I square by 2. So power reduces to half. So this is the higher cutoff frequency, lower cutoff frequency, this is higher, this is lower. Cutoff frequencies are the frequencies where power in the resonance circuit is at least half of the maximum value, or cutoff frequencies are the frequencies at which current in the resonance circuit is 1 by root 2 of the maximum value, power is half of the maximum value. Okay, so okay, right now? So these things are very clear. So resonant frequency, what is bandwidth? The difference in the frequencies of higher and lower cutoff frequencies is called bandwidth. The difference in that frequency. So every TV station or TV channel will be given a bandwidth. So you can communicate your signals from so many megahertz to so many megahertz. That is its bandwidth, and it works between those two. Whereas for radio communication, one frequency is enough. It is very sharp. So quality factor or sharpness of resonance. Now we will derive the equation for it. Okay. How do we derive it? We know that IM is equal to Vm by Z. In any series resonance circuit, the peak value of current is equal to peak value of voltage divided by impedance of the circuit. This is the condition in any case. It need not be only at resonance. If it is at resonance, you know that Im maximum, where is it? Im maximum is equal to Vm by R, because Z becomes equal to R. So at resonance, Im maximum equal to Vm by R, because Z equal to R at resonance when X equal to XL. Correct? All these things you know. Okay, I'll take a new chalk. Right. Now, Im maximum is equal to Vm by R. Now, Im is equal to Vm by Z. Let us expand this. Im is equal to Vm by root of R squared plus, now, I will select a frequency, okay, omega c, you know, this one, Xc minus XL whole squared. Xc is 1 by omega c, XL is omega L. If you want to write this formula, root of R squared plus omega c minus 1 by omega c minus omega L whole square, because Xc is 1 by omega c, XL is omega L, you know that. I will write that formula here, but when I write that formula, let me write this formula Im, that is some amount of AC current, its peak value. It is not the highest peak value current, it is some value of peak current. For example, this current, this situation, I will exaggerate this situation now. When the frequency is above the resonant frequency, current drops, but it drops to 0.707. That means 1 by root 2 of the maximum value. This current is Im maximum by root 2, right? It drops to 1 by root 2 of the maximum value at a frequency omega 1. It is not as much as highest current. Now let me concentrate on this omega 1. What is the Z value here? It is not like Z value here. Here the Z value is equal to R. It is the least value of Z. Here the Z value is this value. Shall I write it? And but remember here XL is greater than XC. So how will be the formula? XL minus XC whole square. But even then, if you write it as XC minus XL, no problem, because you know that even negative, its square makes positive. But we will write the proper equation. Now I am writing the current equation for a situation when the frequency is omega 1. At omega 1, what I can write? Im is equal to Vm by Z, R squared plus omega L minus omega 1 by omega c whole square. XL minus XC whole square. I'll write it like this. Im is equal to Vm divided by root of R square plus, what is XL? Omega L minus 1 by omega c whole square. Hope you have followed this. Now what is this Im at that moment? At the moment of higher cutoff frequency, the frequency more than resonant frequency where the current is at least 1 by root 2 of the maximum value. If the highest current is 10 ampere, now the current flowing is 10 ampere into 1 by root 2. That is 7.07 amperes. At that frequency, what is that current flowing through the circuit? That is nothing but Im maximum by root 2, right? This Im is nothing but Im maximum by root 2, isn't it? This is Im maximum by root 2. Now what is Im maximum? Im maximum is nothing but Vm by R. So internally you have to go on substituting. So I will retain this one now. I will leave this one. I'll write only this one, right? Im is equal to Vm by Z. Z is this much. This is at, okay, I have to write this as omega 1L, omega 1C, because at omega 1 I am writing, right? At frequency omega 1, the total impedance will be 1 by omega 1c, other side omega 1L first, because in this region XL is greater than XC. Omega 1L minus omega 1 by omega 1c whole square, and this Im is nothing but Im maximum by root 2. What is the next step? I'll write it here. Okay, my cable, yeah. Im maximum by root 2, maximum by root 2 is equal to Vm divided by root of R square plus omega 1L minus omega 1 by omega 1c whole square. Now put this Im maximum here. Im maximum is Vm by R, because Z becomes minimum. Vm by R, that is Im maximum. Okay, this much. By root 2 is remaining. Hope you have followed. Because peak value of highest current, highest peak value, it occurs when Z becomes equal to R. Im is equal to Vm by Z is the common formula, but Im maximum is Vm by R. So Im maximum is Vm by R by root 2 is equal to Vm divided by root of R square plus omega 1L minus 1 by omega 1C whole square. This is minus Vm gets cancelled. Numerator is 1, so compare this. Other side, this side. What you will get? R root 2 is equal to root of R squared plus omega 1L minus 1 by omega 1C whole square. Square it now. What you will get? This square root goes, and here you will get 2R squared. 2R squared. I don't want this one now. Okay. 2R square is equal to, right? This is okay now. 2R square, square this. R square plus omega 1L minus 1 by omega 1C whole square will remain. Now I will make little bit space here, and then I will continue. I will rub this and make myself some room here, and then I will continue. And you know that this is of course 2R square and is equal to R square plus omega 1L minus 1 by omega 1C whole square. Now we bring this R square here. 2R square minus R square, that is R square is equal to omega 1L minus 1 by omega 1C whole square. Get the square root. R is equal to omega 1L minus 1 by omega 1C. No square. Okay, now what is this omega 1? Omega 1 is the frequency at which the current in the circuit drops to 1 by root 2 of the maximum value, and that frequency is above the resonance frequency, and that omega 1 is nothing but omega naught plus delta omega. Delta omega is the bandwidth. Omega naught plus delta omega. Can I expand it as omega naught plus delta omega? R is equal to omega naught plus delta omega, okay, into L, this omega 1 minus 1 by this omega 1. Omega naught plus delta omega into C. Correct? What else? Okay, now try to get omega naught L outside here. Omega naught L, if you want to take omega naught L, omega naught outside, then there should be common omega naught. So here multiply and divide by omega naught. Here multiply and divide by omega naught. What you will get? R is equal to, you can understand it now. Omega naught L, I will take it outside. L is however outside. This is 1 plus delta omega by omega naught. Omega naught L plus delta omega by omega naught. Now we bring this omega naught inside. Omega naught plus this cancel, delta omega. Minus here also, minus 1 by omega naught C minus 1 by omega naught C into 1 plus delta omega by omega naught. Okay? Hope you have followed. This also, C is however outside. Omega naught, you bring it inside. Omega naught plus this cancels delta omega. Okay, that step is over. Right. We'll have to write it now here. Right. What is the rest of the thing here needed? R is equal to. Shall I rub this also so that I will get enough space again? This is not needed when intermediate steps not needed. Okay. Right. R is equal to omega naught. Here one more substitution. You know that omega naught is equal to 1 by root LC somewhere, resonant frequency. If omega naught is 1 by root LC, square it, omega naught square is 1 by LC. You bring 1 omega here, 1 omega here. Omega naught L is equal to 1 by omega naught C. It is simply XL is equal to XC. That is what is at resonance, right? Omega naught L is equal to 1 by omega naught C. So shall I replace this 1 by omega naught C by omega naught L, so that everywhere you have omega naught L. So what is R? R is equal to omega naught L into 1 plus delta omega by omega naught and minus 1 by omega naught C is nothing but omega naught L divided by 1 plus delta omega by omega naught. But this remains in the denominator. This part remains in the denominator. 1 by omega naught C is omega naught L. Rub this. This you can follow because it is XL equal to XC. That's all. Okay, now here you have to use a binomial expansion. I think you have to bring this up. You know that when x is here, x to the power minus 1. R is equal to omega naught L 1 plus delta omega by omega naught minus omega naught L into 1 plus delta omega by omega naught to the power minus 1. 1 by x, x to the power minus 1. Now you have to expand this. You know that 1 plus x to the power n is almost equal to 1 plus nx if x is much less than 1. If x is a term which is much less than 1, then 1 plus x to the power n is almost equal to 1 plus nx. Otherwise you will have, if x is not less than 1, you will have 1 plus x squared by 2 factorial plus x squared by 3 factorial, so on, right? You will have a long term for that. Now this, you see, delta omega by omega naught is much less than 1, because always this bandwidth will be very less, but resonance frequency will be very high for the resonance circuits used in communication, especially. In radio communication, TV communication, we use very high frequencies for communications, but bandwidth is very less compared to that. You will have some few thousand hertz bandwidth, but the resonance frequency will be gigahertz and megahertz. So when it is so, since delta omega is very less compared to the resonant frequency, this is much less than 1. So what I can write? R is equal to omega naught L into 1 plus delta omega by omega naught minus omega naught L into 1 minus 1 plus nx, n is minus 1, 1 minus delta omega by omega naught. So what you will get? Omega naught L common. R is equal to omega naught L into common omega naught L, 1 plus delta omega by omega naught, this one, minus 1 plus delta omega by omega naught. Okay, this gets cancelled. 1. R is equal to omega naught L. What you will get? 1 this plus this, 2 delta omega by omega naught. Yes, you just bring this here, and omega naught by delta omega, that is what we need, right? Omega naught by delta omega. Bring this here, omega naught by 2 delta omega, resonant frequency by bandwidth, total bandwidth 2 delta omega is equal to omega naught by L by R. You have got that. Sir, how do you get this one? You just change it from here. Instead of substituting omega naught L as, 1 by omega naught C as omega naught L, you substitute omega naught L as 1 by omega naught C. Then you will end up at omega naught C, 1 by omega naught C R. That's all. So that is the resonant, quality factor. And more the quality factor, lesser is the bandwidth. And it's a very sharp circuit. I think you can understand it, right? We have discussed it. It's a very sharp circuit. For radio communication, this is needed. The radio, once it is set for one frequency, it has to receive only that frequency signals. It shouldn't receive any frequency very close to it. It should reject them. So it's a sharp selector, quality factor is high, bandwidth is very less. So that is the meaning. And quality factor has no unit, because reactance by reactance, ohm cancel, frequency by frequency, no unit for quality factor. It is simply a index, right, to show if more quality factor, higher is the sharpness, and lesser is the bandwidth, and less quality factor, more will be the bandwidth. So that's about the derivation. Hope you have followed. It's a long derivation. Board is not enough, so I have to rub and digest it somewhere here. Thanks for watching this class. This is not very much needed for the exam. They won't ask you for the derivation. But better is learn it so that you will get the idea what we are doing here, and the resonance circuit becomes very, very clear to you, because now you have understood what is this frequency, at that frequency what happens to the current, at this frequency what happens to the current, why do we select all these frequencies, and because it has to operate between these two, so where it is selected and all this. Thanks for watching the class. We will meet in the next class with one more derivation, right? That ends the theory of that chapter. Thank you.